Perfect. So today's talk is called Algebraic Topology in a Nutshell. That is less because I'm going to explain the whole of what algebraic topology is, and more because I didn't know a week ago what the content of the talk would be. So maybe I'll focus more a bit on the topology part, and I will not precisely explain what the algebraic part in this field of algebraic topology is. Yeah, algebraic topology is the field of mathematics in which I'm doing a PhD. So let's start. Right. There is geometry and there is topology, and they both study shape, if you want. Because as a first thought, I would say that topology is the study of shape in some sense. And you might ask, right, isn't that geometry? And right, in geometry, of course, we know there are shapes like triangles, squares, circles. They have areas and angles, right? And we can measure all that, like distances, areas, angles. You can ask questions like, can you square the circle? And that makes sense there. I will explain in a second why in topology this is not even a valid question. You can ask questions like, what's the distance from the Earth to the Moon? And that has a very precise meaning in that picture, right? It's that distance there. Or you can use geometry to explain how the universe is curved, etc. But in topology, our motto will be that we do not care about distances. Okay, so that's the main difference between geometry and topology. It's the study of shapes when we do not care about distances. Right, so what does that mean? It means that we consider most of our shapes that we speak about to be made out of elastic materials. Okay, so for example, if you had a disk that looked like that, you can sort of shrink it inwards. Just imagine it being elastic or made out of plastiline. You can sort of push it to form a smaller square, or for that matter, you can conceptually, if you do not insist on it having the same volume, you can shrink it all the way down to a point, to a single point. And right, if I ask about the Earth and the Moon, as I asked before, well, you can shrink the whole of the mass of the Earth, at least in my topological mind, to a single point. Same for the Moon. And you can move them around. So this for me is the same picture as that. Well, there's a smile there. And I do not care about the distances in between. Similarly, if I walk on land, right? Like, for example, if this is a map of two islands, I don't know what they look like, but two random islands, and the blue part stands for water, sea, or lakes. And I'm not allowed to step on the water because I don't know swimming, for example. And I'm trying to understand the topology of this. Since I do not care about distances, this picture on the left is precisely the same as this picture on the right. Okay, this color is not rendered well. It's supposed to be blue. That's supposed to be the sea, but that's fine. And so, in this picture, you can definitely say that this island is smaller than this one. But since I don't care about distances, I can just stretch it out, make it into any shape I want. And all I care about is that there's a forbidden region in the middle. And on the island on the right, there are 3 forbidden regions that I'm not allowed to step on, that are the water, essentially. Right. So what can we tell if we do not speak about distances? Then we lose lots of information, right? We cannot measure angles or areas or distances. So what is left? Right. For example, what is left is that on the picture on the left, you can say that you cannot move from a point here to a point there. There's no possible way of going if you do not make a bridge or invent a ship. And that's preserved in the picture on the right. You cannot go from here there. So that means that that shape of these 2 islands is not connected. So that's a first step. We can speak about the shape being connected. If you can move from one point in it to another point. Right, so we started speaking about paths, or rather, right. So if everything is made out of elastic materials, this is a common joke, that a topologist is a person who cannot tell the difference between a coffee mug and a donut. And this is a visual representation of that joke. Because if you allow it to be made out of plastiline, then you can deform one into the other. Right. So then, what do we have? What can we tell? Let's speak about paths. This is my impression of the fields of Churchill College. I currently live at Shepherd's Flats, and I go to my department, that is the CMS, and I have to cross the fields of Churchill College to go. And I usually take a route like that. Now, like if like in the beginning, I was following the rules, and I started by walking along the path that goes around. Right. That was one way of crossing the fields of Churchill College. But soon laziness got the better of me, and I started taking a path that it was more and more straight line. And Pythagoras will remind us that the diagonal will be the most the quickest path. So it suggests that we should use that path. But on days that I'm not in a hurry, I might even I might be thinking, I might be strolling, and I might start and then, stop here for a bit. Then maybe walk back because I think that I forgot my keys. And then eventually, right, this wants something else from me. And then eventually decide to head back to the department. But right, are all these paths, different for a topologist? The answer is no. Because if you imagine them made out of, long ropes made out of rubber, and you fix them here and you fix them there, and then you just pull them to be tight, then all of these can be sort of deformed to any of the other. They can be deformed to the path that is a straight line path if you just pull hard enough. As I said, I'm a topologist. Everything for me is made out of elastic material. And since there is no forbidden region, if you want, then any path that I might take can be straightened to the straight line path. Okay? So let's make some definitions. For the sake of the argument, it's better to think about paths that start from here, go, and then come back. Okay? So loops are paths that start and end at the same point. So, and we say that two loops are homotopic if they can be deformed to one another. That practically means exactly what I showed you in the picture in the previous page. Any, like this blue path that goes like that, and this straight line path are homotopic because you can pull one as if they're made out of an elastic material to the other. And a path will be contractible if it can be homotoped to the standstill path. This is just the path that you spend your whole time here, and you never ever leave that point. And for example, the path that goes, any path here, any loop here, you can sort of shrink it down to the standstill path. So here on the Churchill College fields, every loop is contractible. Of course, the situation would be totally different if we were on the grounds of Trinity College, where you're not allowed to step onto grass, and so you would be forced to remain on this surrounding area. And I think you would agree with me that this path that goes around, you are not allowed to contract it through here continuously because you're not allowed to step on grass. Okay, right. So let's see. Let's speak exactly about the situation that I just described. Suppose we've got a court that looks circular like this, and it has a fountain in the middle that you're not allowed to step on, and it has only one entrance and exit here. And right, a person is allowed to enter, walk around, and then stroll, and then eventually go out. Okay, and then he leaves a trace of his path. He leaves a rope there, and then that rope, somebody here at the entrance pulls it down all the way here. And for example, this rope would be able to pull it all the way down to stand still, like all the way to the entrance, because it doesn't go around around the central fountain, right? If you go around the central fountain and somebody pulls the loop here, it would get smaller and then smaller, but it would stop, like it wouldn't be able to go all the way without bringing down the fountain. So we can ask questions like, which loops are contractible? That is, which loops can be pulled back to the entrance? And like the answer is to that, the ones that do not go around the fountain. Right. So how like this seems reasonable to explain, right? And you can even do something more. You can even start from here, go around. You can go many times around. I think I went 3 times around here and I went back. So this path went 3 times around. And so when you pull, then the rope will tighten around the fountain 3 times. This path would just tighten around once, or this path that goes like that the other way would tighten around once, but in the opposite direction. Let's call it -1 path. So it might be a reasonable question to ask, how many, like if for me homotopic paths are the same, how many different paths are there? Right, and the answer is precisely this, that you understand them by asking the question, how many times? The answer to the question, how many times did you walk around the fountain? Right. And bear in mind that somebody could walk around once, come here, walk around once, but then just decide to go backwards all the way. And that for me would count that he walked once around and then minus once. That counts as 0 times for me. And if you walk around 0 times, then this loop can be contracted. Like if you pull this rope, it can go all the way back to the entrance. Right. Let's speak about this. Let's try to visualize this a bit better. And let's speak about the infinite spiral staircase. I want you to focus with me on this staircase here. If you look on this from above, it would look precisely like the court, right? It would look like a circle, and then minus a circle in the middle, and you're allowed to walk around. It's just that if you walk around once, then you end up at the same point. But remember, I do not care about distances. So I'm sort of allowed, right, as a topologist, to go and unspiral, if you want, this infinite staircase to get this straight staircase. And in fact, I can flatten it down to get this infinite corridor here. Right. And right, this corridor pretty much looks like the Churchill fields, in that if you start from a point and you walk any path around and end up at another point, then, and you leave a rope behind, an elastic rope behind where you went, then you can just pull this rope and make it go straight. So practically, every path between 2 points is homotopic to just a straight line path. Right. So this is the same for the staircase that goes upwards, and this is the same for the staircase that is spiraling. If you start from this point down here and you walk around and then walk backwards to this point, then you can pull your rope to just be the straight line that goes from one to the other. So where do I want to get with this? Let's move on to the next picture. Let's put this staircase and this court, whose entrance I've drawn on the right this time, and imagine that we've got 2 people. Let's draw one guy here greeting us. No, let me make him white. That will be more visible. He looks like holding a sword, right? And let's put another guy here. And these guys communicate with each other. So guy, let's call this guy, let's call her Alice, and let's call this guy Bob, okay? So Alice walks around the fountain. And as she walks, she speaks through a walkie-talkie to Bob and tell Bob, oh, I'm walking anti-clockwise. Sorry, I'm walking clockwise, or I'm walking anti-clockwise. and Bob does the same on his infinite spiral staircase. Now, so what happens if Alice just walks the path that I've drawn below? Bob starts from his 0th floor. Let me write it here. Let's call this floor 0, ground floor, first floor, second floor, and then -1, -2, and it goes downwards and upwards. So Bob follows Alice's advice. He walks first a bit that way, then Alice decides to go backwards, right, whoop, and then he goes all the way up. Right, so Bob ends up there when Alice goes along the circle and ends up back at the entrance. So what has happened with Alice? Alice ended up at the same point that she was, but Bob ended up 1 floor upwards. So that happens to coincide with the fact that if you pull this rope of Alice hard enough, it will end up looking like this rope that I just drew, that goes precisely once around the fountain. So what I want to get to with that is that if Alice does any path and does this process with Bob, and then pull the rope back to homotope it to a simpler path, and do the same here in the situation with Bob, the number of times that Alice's rope goes around the fountain, this just equals the number of floors that Bob goes up. And that essentially, and that because we know that in Bob's world, every 2 paths from between 2 points are homotopic. This answers a question of classifying all paths in Alice's world up to homotopy. They just have to do with how many times you go around the fountain. So essentially, out of this, what we have shown is something that one shows in the first few lectures, like the first triumph of algebraic topology in every algebraic topology course, that you compute the so-called fundamental group of the circle to be Z, to just have to do with how many times you go around. I will not speak more about this, but in practical terms, and both the proof and the content of what we've done is precisely this game between Alice and Bob with the court and the staircase. Right, now if we wanted to classify paths in a more complicated world, like the Trinity Great Court, that we're not allowed to walk on this grass, nor that grass, nor any of these 6 patches of grass, and we just started walking around, just knowing how many times you went around each of these 6 courts wouldn't be enough to classify the path. That will be much more complicated, and well, that's another story, but that's a story that we answer soon enough in algebraic topology. Right, so where do we go from after this? We managed to show something about some topological spaces, to show, for example, that there's a basic difference between this shape that has this forbidden region and this shape, because here all loops are contractible, but here not. But what more can we say? Right, we can do more things. Instead of just putting ropes in them, we can put, if you want, balloons in them, or spheres, or higher dimensional spheres, and find more. Like compute more things. They become increasingly complicated, but they help us understand more complicated spaces or shapes. And right, yes, there was a picture here that I couldn't render, so that's why there was space there. So as a final comment, you can ask, where do more complicated spaces appear? And right, like an application of algebraic topology is this like famous Harry-Pohl theorem that literally says that if you've got a ball where hair comes out and you try to comb it so that it goes flat, it cannot. And this is summarized in this picture, but this corresponds to the fact that on the head of everybody, there is this point on the back where we don't have hair, because if we had, it would just point outwards. This can sometimes be called why at any given point there's a tornado on Earth. Right, another place where this appears is in knots, because right, if I'm allowed to, like the question with a knot, for example, the knot drawn here would be, right, if I pull this knot, does it get undone, or is it a good knot? And like, remember that in algebraic topology, we're allowed to pull things. So if I say you're allowed to pull this, but it shouldn't never cross itself, then I'm asking the question essentially, is this a good knot? And there's a branch of maths called knot theory that applies algebraic topology to classify and understand knots. But this also appears in large data sets where you've got many high dimensional problems to solve, and right, you want to know, do my data as drawn here lie on a line, a circle, a sphere? But if this is in much higher dimensions, then this picture is not enough to tell you the answer, because you cannot draw a picture that you can see. So how would you be able to answer this question? What is the shape on which the data lie? And there is this branch of algebraic topology that is very recent, and right, it hasn't done much, but it actually has done a couple of interesting things called topological data analysis, where they apply some methods to large data. And yeah, so and I think I will stop here. I try to put algebraic topology in a nutshell, because I do not care about distances. I can just, I could shrink it and put it in a nutshell. That's a bad joke. But yeah, I think I will end here.